In last lecture, we have seen there are some vectors when pre-multiplied by matrix A, then A into X is their scalar multiple. So let us define what exactly those type of vectors are. So let P is a linear transformation from Rn to Rn with standard matrix A. Clearly this matrix will be of order n cross n. So with this prerequisites, a vector x belongs to Rn, and that vector we are taking as non-zero vector. So a non-zero vector x belongs to Rn is said to be eigenvector of A if there exists lambda belongs to R such that A into x is equal to lambda x, and such a lambda is called as such a lambda is known as eigenvalue of E. So we say that x is an eigenvector of A corresponding to eigenvalue lambda. Corresponding to an eigenvalue lambda. Okay. So now given a linear transformation and its standard matrix, the immediate question arises: how do we find such a x and such a lambda? So given a matrix A, how to find possible eigenvalues and possible eigenvectors? So if I just look at equation star, let's try to find out standard algorithm how we find x and lambda. So this A is n cross n matrix, this x is n cross 1 column vector, lambda is a real number, and this x is n cross 1 column vector. So for a moment what we do, this lambda, let's multiply or let's rearrange this term lambda into x as I into x, and this is justifiable where I is n cross n matrix, identity matrix, and this is n cross 1 column vector. So what I can do now, this rearrangement or this rewriting of the lambda x term gives the further representation as A into x minus lambda I into x equal to 0. And now if I rearrange, so x can be taken common, A minus lambda I into x equal to 0. The reason behind doing this rearrangement, now this subtraction is well defined. A is a square matrix of order n, and this lambda into I is also a square matrix of order n. So ultimately this bracket is a square matrix of order n, and that is pre-multiplied to column vector of Rn. So now our problem of finding x and corresponding lambda has been reduced to solving this system, and you can observe that this is a homogeneous system because right hand side term is a zero vector. And if you just recall, in the starting only I said we want non-zero vectors. So basically I want non-trivial solution to the system represented by equation 1. So when we get non-trivial solution to this system 1, so from our previous knowledge, it is very clear that non-trivial solution of non-trivial solution of 1 exists if and only if determinant of, or let's say first of all, if and only if rank of A minus lambda I is strictly less than n, and that is equivalent to saying that if and only if determinant of A minus lambda I is equal to 0. This we have seen in the starting. For a square matrix, for determinant to be 0, we must have rank less than n. So this is what condition we derived, determinant of A minus lambda I equal to 0 for existence of non-trivial solution to the system 1. But this is actually equivalent to finding non-zero x which satisfies the condition Ax equal to lambda x. So this equation is actually called as, this equation is known as characteristic equation of E. Characteristic equation of A, and if you observe that left hand side of this equation, left hand side of this equation is going to be a polynomial in lambda. LHS of this equation is a nth degree polynomial, is nth degree polynomial in lambda, is the nth degree polynomial in lambda. This polynomial is known as, this polynomial is known as characteristic polynomial, characteristic polynomial of E. So let me say it again. This equation number 2 is known as characteristic equation of E, and the left hand side, which is a polynomial in lambda, is known as characteristic polynomial of E. So if I solve this equation, determinant of A minus lambda I equal to 0, we are going to get values of lambda, or basically roots of the above equation. roots of characteristic equation are nothing but roots of the characteristic equation are nothing but characteristic equation of A are the eigenvalues of A. Eigenvalues of A. So once we solve the above equation, we are going to get eigenvalues of A, and further let's see how we are going to find eigenvectors of A corresponding to that eigenvalue lambda. And it is very clear that if the matrix if the characteristic polynomial is of n degree, we may get at most n roots to the polynomial, okay, or n roots to the characteristic equation. So let's see exactly how we are going to find those eigenvalues and corresponding eigenvectors. So here in the starting, let me just correct here. T is a linear transformation from Rn to Rn. T is a linear transformation with a standard matrix A, whose order will be n cross n. So with this A, which is a square matrix, we are interested in finding x such that Ax is equal to lambda x. So this problem of finding x and lambda has been reduced to solving this non-homogeneous system. And as we are interested in the non-trivial solution, we must have determinant of A minus lambda I equal to 0. And if you just recall the concept of null space, you can see here we are interested in finding non-zero x such that this matrix in the bracket into x equal to 0. So actually we are interested in finding null space of A minus lambda I. Null space of A minus lambda I will be all x in Rn such that A minus lambda I into x is equal to 0. Corresponding to the particular value, okay? corresponding to particular value of eigenvalue lambda. Let's will you focus to this particular term later also.